Control computers with muscle signals. Non-invasive EMG wristband breakthrough. Imagine a world where your thoughts can seamlessly control technology without the need for traditional input devices. This is the promise of a groundbreaking non-invasive neuromotor interface designed for human-computer interaction, which has the potential to revolutionize how we interact with our devices. But here's where it gets controversial. While many existing input methods like keyboards and touchscreens have their limitations, this new interface aims to eliminate those barriers, especially in situations where conventional methods are impractical. Published on July 23, 2025, by Patrick K. Fosh, Thomas R. Reardon, and the Control Labs team at Reality Labs, this research article explores the development of a versatile neuromotor interface that utilizes surface electromyography, sEMG, for decoding computer inputs. The goal is to create a system that is not only intuitive and expressive, but also universally applicable across different users. Since the dawn of computing, there has been a quest for input technologies that are both expressive and user-friendly. Traditional devices like keyboards and mice, while effective, can be cumbersome, particularly in mobile scenarios. Gesture-based systems have emerged as a solution, using cameras or sensors to interpret movements without the need for physical devices. However, these systems often struggle with occluded movements or poor lighting conditions. In contrast, brain-computer interfaces, BCIs, that tap directly into the body's electrical signals have been proposed as a solution to these challenges. Yet, most high-bandwidth BCIs have relied on invasive methods tailored to individual users, which limits their accessibility and practicality. This new research introduces a non-invasive neuromotor interface that leverages sEMG technology, allowing for the decoding of computer inputs from muscle signals. The team developed a highly sensitive wristband that can be easily worn and a scalable infrastructure for gathering training data from thousands of participants. This extensive data collection enabled the creation of generalized sEMG decoding models that work across different individuals. In tests, users achieved impressive results. A median performance of 0.66 target acquisitions per second in continuous navigation tasks, 0.88 gesture detections per second in discrete gesture tasks, and a handwriting speed of 20.9 words per minute. Notably, the performance of handwriting models improved by 16% when personalized to individual users, showcasing the potential for tailored applications. The implications of this research are significant. As interactions with computers become more prevalent, the need for input methods that balance portability, efficiency, and accessibility is paramount. This new interface could facilitate seamless input for mobile devices like smartphones and smart glasses, making technology more accessible to everyone. However, the journey to a fully functional neuromotor interface is not without its challenges. Current EMG systems face limitations such as cumbersome wiring and discomfort during use. Moreover, achieving consistent performance across different users and sessions remains a technical hurdle. To address these issues, the researchers focused on a non-invasive approach that reads electrical signals from muscles. By utilizing sEMG, they were able to achieve a high signal-to-noise ratio, allowing for real-time gesture decoding without the complications associated with visual-based systems. The results of this study pave the way for future research and development in sEMG-based human-computer interaction. The findings suggest that it is possible to create a high-bandwidth neuromotor interface that generalizes well across different users, potentially transforming how we interact with technology. As we look to the future, the potential applications of this technology are vast. From enhancing accessibility for individuals with disabilities to creating more intuitive interfaces for everyday users, the possibilities are exciting. But what do you think? Could this technology change the way we interact with our devices? Or do you believe there are still significant barriers to overcome? Share your thoughts in the comments. Meta's gesture control wristband, transforming computer interaction. Here's a truth about financial models that many investors overlook. The numbers you see on paper don't always reflect real-world outcomes. But here's where it gets controversial. What if the very tools we use to predict the future are built on assumptions that might not hold up when the market turns volatile? Let's break down the fine print behind backtested performance metrics and why they're both fascinating and frustrating for beginners. The TipRanks Smart Score, for instance, relies on historical simulations to showcase its strategy's potential. But here's the catch. These simulations are like a dress rehearsal for a play that hasn't been performed yet. They assume perfect conditions, like a market that's always liquid, meaning you can buy or sell assets instantly without affecting prices, and a world where the model's recommendations could have been executed flawlessly. And this is the part most people miss. The models are often tweaked after the fact to look better in hindsight. Imagine a chef claiming a recipe is perfect because they adjusted the ingredients after tasting the final dish. That's essentially what backtesting allows. Security selection methods can be fine-tuned until they produce the most impressive historical returns. But does this mean the models are just being tweaked to look good in hindsight? The disclaimer warns that actual performance might differ wildly. For example, if a market suddenly becomes illiquid, think of trying to sell a rare painting during a global crisis. The model's assumptions crumble. And let's not forget the hidden costs. Fees, transaction expenses, and management charges aren't included in these simulations. It's like planning a road trip based on a map that ignores gas prices and tolls. So what's the takeaway? These backtested results are useful for understanding how a strategy might work in theory, but they're not a crystal ball. The real test comes when the model faces unpredictable events like black swan crises or sudden regulatory changes. Do you think these simulated results are a reliable guide for real-world investing, or are they just a misleading illusion? Share your thoughts in the comments. Let's debate whether we should trust models that thrive on hindsight but struggle with foresight.